So, in the previous mini lecture, we discussed the physiological adaptations that occur as a result of endurance based training. Now, we're going to look at how those adaptations result in a change in performance. So, how is endurance or cardiovascular performance, both for a general population individual and an elite athlete, how it is affected by all that training and those adaptations that occur? The three adaptations that influence and affect endurance performance are, first of all, your maximum aerobic capacity, and this is also known as your VO2 max or VO2 peak, the maximum volume of oxygen that you can take up, deliver, and use within 1 minute. Second of all is your metabolic efficiency, how efficient your body is at utilizing oxygen for energy production. And thirdly is gross mechanical efficiency. So we cannot directly assess your internal changes. We can't take a muscle biopsy that easily, or we can't put biopsies in the heart and see how changes in stroke volume happen. It's a lot harder than it looks. So what we do is we can assess external performance improvements. We can assess changes in your VO2 max, changes in metabolic efficiency, and changes in gross mechanical efficiency to get an idea of how the adaptations have translated into improved performance. So the goal of endurance training really is to improve system tolerance and capacity. So it's all about delivery, uptake, and use to improve these three performance and outcome variables. So now let's talk about the first performance change that you see with endurance-based training, and that's changes to your maximum aerobic capacity or your VO2 max and peak. And I know you've talked about this before in exercise physiology, so we won't talk about it too much, but there is a strong correlation between all-cause morbidity and cardiovascular fitness level or health, such that if you have a higher cardiovascular fitness, your risk of all-cause morbidity is decreased. So high aerobic capacity has also been shown to be favorable for endurance performance, that those who have a high aerobic capacity can take up, deliver, and use oxygen more efficiently than someone else, and therefore they'll be better at endurance-based sports. As well, what's been shown in the literature is that VO2 peak increases 10 to 30% with aerobic training within the first 6 months of endurance or aerobic or cardiovascular training. So that's quite substantial. There's a large range there, 10 to 30%. Obviously, the person who has never, the sedentary individual that starts a cardiovascular program will be on the higher end, probably around the 30% mark, while an individual who is already endurance trained may be more like a marginal gain, even a 2% change. But that might be the difference between a podium performance and a mere finishing result when it comes down to elite sports. So a key point here is that physiology drives the performance change. So on the left figure, we see VO2 max over cardiac output. So there's a direct relationship between an increase in cardiac output, how much your body can, or your heart can eject from the left ventricle in liters per minute, and VO2 max. So the increased capacity of the heart and the strength of the heart increases VO2 max, so we have greater delivery. While the middle figure shows a strong correlation between hemoglobin, HB, hemoglobin mass, and VO2 max, such that as hemoglobin mass in the blood increases, so does VO2 max, because this is your taxi, remember. So now we have an enhanced delivery of oxygen to the working muscle. And lastly, we see a strong correlation, not as strong as the previous two, but still a relatively strong, significant correlation between the increase in blood volume that happens with endurance training and VO2 max. So as we can see, physiology drives the change in VO2 max. We have increased strength of the heart, we have increased ability to transport oxygen, and we have a greater amount of blood volume. And these all are closely correlated to an increase in VO2 max. So physiology is tied to the performance change. So this figure showcases the percent improvement in VO2 max on the y-axis and training intensity as a percent of VO2 max on the x-axis. So this is the relationship between training intensity and improvement in VO2 max. So there's two things I want you to see here. Firstly, the greatest improvement in VO2 max happened with higher training intensity. So the rationale, and this is really the rationale for endurance training, as you cannot maintain a high intensity for a long period of time, but you can do intervals with rest periods. So as you can see, greatest improvement in VO2 max of around almost 33% happened at a training intensity between 80 to 100% of your VO2 max. Second of all, the lower intensity, so 50 to 70% of VO2 max, when you trained at this, you still see improvements. So this is good for an elderly individual where intervals are not preferred. So there are slower improvements made, but there still are improvements. So this is really good because one, we see greater improvements at higher intensity of exercise, hence the reason why we have high intensity interval training. But we also see improvements in cardiovascular health and VO2 max as a result of lower level intensity. And therefore, we can recommend cardiovascular training to whatever population. It's just the rate of return will be affected depending on the intensity that we prescribe. Okay, so now let's move on to metabolic efficiency and gross mechanical efficiency. Remember, the goal of endurance training is to improve the system's tolerance and capacity through delivery, uptake, and use to improve these three specific performance variables. Now let's discuss metabolic efficiency. This is about how efficient your body is at producing energy. So remember, one adaptation that we noted that happens with endurance-based training is an increase in the mitochondria within your cell. So if you have more mitochondria, you can actually use that oxygen because you have more Krebs cycle and electron transport chain happening. So now with more mitochondria, we can use more free fatty acids, as well as we're more efficient at using glucose as an energy source because we have the Krebs cycle and electron transport chain. One technique used by exercise physiologists to showcase changes in metabolic efficiency is blood lactate profiling. So this is when you get an individual to sit at multiple different exercise intensities, progressively going upwards, so it's getting harder, and you take a blood lactate sample from their fingertip with the capillary sample from their fingertip, and you measure their blood lactate. And as you can see here on this figure, we see that blood lactate response is on the y-axis and speed or power is on the x-axis. And as one becomes more endurance trained, we see a right shift in this curve from the red line to the black line, and eventually with more training to the green line. And so we see this right shift in the blood lactate response such that there's less glycolysis happening, less production of blood lactate as a result of the same exercise intensity. So this means that the body is more efficient at using glucose and free fatty acids as energy sources, and as a result, there's less blood lactate being produced. Now we're going to discuss the third factor, and that's gross mechanical efficiency. And anyone who swims can attest to this. Before I took any swim training classes, I was so inefficient at swimming. I would waste so much energy trying to move a certain distance. It wasn't until I worked on my stroke and my stroke rate and my biomechanics of the stroke, and then I became more efficient at pulling water and had less energy leaks. So this is really important. So gross mechanical efficiency affects, it is an adaptation to endurance training. The more you do something, the more efficient you become at it if the movement pattern is correct. When it comes to gross mechanical efficiency, there's one question I always ask. How efficient are you at moving? And this directly affects your rate of fatigue, your caloric expenditure, and your perceived effort. So I always go back to the analogy of the paddle boat. When I'm in a paddle boat, it's extremely inefficient. And maybe if you haven't tried one before, you should, because you're using your legs to cycle this little thing in the bottom of the boat, and you're hardly even moving. And you have to put in so much energy to try to get across the lake or get across to wherever you're going, and it's highly inefficient. There's a lot of input for very little output. Another example is my first car, my Volkswagen Jetta up there in 1989. I remember getting it when I was 16. And to fill that tank, the gas tank up, it was $15. And that thing would go for like 1,000 kilometers. It was amazing. It was highly efficient. The engine was extremely efficient. I wouldn't say it was powerful, but it was efficient at utilizing the gas and combusting it to produce energy for which the car could use. So that is an example of gross mechanical efficiency. The actual definition is gross mechanical efficiency represents the link between cellular energy production and actual external performance. So it's input and output. It only is measured by use of direct or indirect calorimetry in conjunction with an output measurement, speed, velocity, or power. More efficient individuals will be able to produce more power and velocity for a lower metabolic rate. So you're producing or expending less calories, but you're moving further. And it varies. Your gross mechanical efficiency varies significantly between individuals, depending if you have disease. For example, an individual's COPD may not be able to get oxygen in, so their cost of breathing is very high. Therefore, their gross mechanical efficiency is low. Biomechanics play a huge role. Someone who's running stride or their gait or their swim biomechanics affects their gross mechanical efficiency. And then genetics also affects your gross mechanical efficiency. So here are some factors affecting human efficiency. One, internally, disease, asthma, COPD affects the ability to take up oxygen, and the cost of breathing is very high. Also, factors affecting VO2 max, so uptake, delivery, and use of oxygen, if there's any type of issue with mitochondria genetically, as well metabolism as an internal factor such as enzyme activity, fuel storage, if you have more glycogen or less glycogen, more fatty acids, less fatty acids, more intermuscular triglycerides, that plays a factor to human efficiency. And then neuromuscular efficiency, so the myelin sheath in the propagation of a nerve impulse also affects human efficiency. And then the external ones, which are a target for lots of innovative projects, is aerodynamics, biomechanics, and equipment. And this has been a target for many sports to try to improve. We can work on the training internally, but the external, there's large gains to be made when we improve aerodynamics. The question becomes, how can we improve movement efficiency? So this slide I always find really interesting. And remember, this is looking at factors affecting aerobic exercise performance that may be further enhanced in already champion athletes. So we're talking about the elite here, that special population. And really all it is about is marginal gains. And the marginal gains could be 1 to 2%. Which aren't that big. But when you're already at the elite level, a 1 to 2% change in training and performance is significant. And that really could be the difference between a podium performance and a mere finishing result. So let's look at this. How much of a change in VO2 max can be made for an already champion athlete? Well, minor potential for further improvement. And what they say is altitude-based training can help with hemoglobin mass improvements. Blood doping has a substantial change. Obviously, that's illegal. O2 extraction has less potential for change. So where do we see the biggest marginal changes for champion endurance athletes? One is in the lactate threshold and critical power. So that's all about metabolism. That's all happening at the skeletal muscle level. So you can see the factors there. Second of all is gross mechanical efficiency. So skeletal muscle fiber distribution, mitochondrial properties, loss of elasticity. We have a lower cost of breathing, and you can also use inorganic nitrate. So those are two things. Gross mechanical efficiency and the lactate threshold can be changed with endurance training in already champion athletes. And obviously genetic factors, we can't obviously change those things. So the marginal gains are really happening to metabolism and gross mechanical efficiency. The last point I want to make on this slide is this is the principle of diminishing returns. That as you become more and more fit and endurance trained, you're going to see diminishing returns in regards to the training you're doing. And it comes down to marginal gains. So a prime example of this is what I mentioned before. A sedentary individual engages and starts on a cardiovascular training program. You see large improvements over the first 3 months, and then it starts to taper off. Well, now you need a greater stress to get over that hump to start to see more changes. However, as you become more and more fit, there are diminishing returns. The large changes won't be as much, and as you become more efficient. This is all about marginal gains. So overall, from what we've covered so far this week, physiology drives the adaptations. So the way that you train is going to cause a stress to your physiological system, which is going to drive the appropriate physiological adaptation. And when it comes to cardiovascular training, it's all about changes in the delivery, the use, and utilization of oxygen with endurance training. This leads to improved VO2 max and peak, metabolic efficiency, and improvements in gross mechanical efficiency. This is extremely important information to know because essentially, when we're looking at assessments for cardiovascular health, we want to assess an individual's response from a VO2 max standpoint or VO2 response to exercise. We want to assess their metabolic efficiency to see how this has changed over time, and also assess their gross mechanical efficiency to really get a snapshot of the underlying physiological changes that have happened as a result of cardiovascular training. A rule of thumb is if you don't use it, you'll lose it. And I'm sure you've heard this before. That ultimately, if you are not doing cardiovascular training and stressing that system, you're going to revert back to the original state. In this, for example, up to 50%, there is up to a 50% reduction in mitochondrial mass after 1 to 2 weeks of detraining. And so what happens is you actually see a decrease in the size of your muscle as a result of a decrease in the density and volume of mitochondria. And this is really because it's too metabolically costly to maintain organelles that you aren't using, that it requires energy, ATP. And so if you're not going to use it, you're going to lose it in order to maintain the central functions, etc., of the body. Now let's go back to one of the slides I posted in the initial stages of this lecture series this week. Why is having a good aerobic fitness level important? And there's 3 main reasons. It's the basis of health. From a cardiovascular, metabolic, health body mass standpoint, lean body mass, it helps in the prevention of many metabolic disorders, and it also is tied to all-cause morbidity. Second of all, it improves tasks of everyday life. Those tasks become more easier as you become more efficient in producing ATP, and so your rating of perceived exertion for a given task is less. And then thirdly, the main reason why having a good aerobic fitness level is important is recovery. Recovery between work shifts, between sport shifts, between sessions, sets, reps. Your body recovers faster from tournaments, from your work demands, multi-day sessions, and ultimately, the aerobic system is a core component of the physical demands for every single sport. Coming back to this slide as well, all these elite endurance athletes or aerobically trained athletes, essentially across all individuals, special populations to general populations, we're all trying to acquire the same physiological adaptations from cardiovascular training. For a beginner who is sedentary at one time, who engages in a cardiovascular training plan, we're going to see greater improvements faster, but with time, we'll see diminishing returns. So as a beginner, you could see 10 to 30% improvement in the first 3 months of being on a cardiovascular training plan. Or for a more elite athlete, it's all about marginal gains. It might be 1 to 2%. And you have to be more strategic in how you are going to acquire those changes because you need to stress to the system in order to see more improvement. The question becomes how much cardio fitness is needed. And this comes back to your needs analysis. When you're working with your client, based on their gaps and where they are classified compared to their competitors, compared to other people that are their own sex and age, how do they compare? And then you determine whether this should be a goal for them to improve their cardiovascular fitness. This is all based on the needs and gap analysis. So in summary from this week's content, first of all, our body responds to specific stress, that chronic shock. So it's not just one-time stress. No, this is chronic stress over time, hence the reason why it takes 8 to 12 weeks to see changes from exercise training. And this leads to specific physiological adaptations in response to that specific stress. Second of all, endurance training leads to cardiovascular and skeletal muscle adaptations that increase delivery, uptake, and use of oxygen and nutrients to increase your aerobic capacity, your lactate profile or your metabolic efficiency, and your mechanical efficiency. which this leads to the goal of cardiovascular training being system tolerance and improving the capacity of the system. So these adaptations result in improvements to general health, tasks of everyday life, reduced risk of cardiovascular and metabolic disorders, and improved and expedited recovery.